So, we may continue now. Are you hearing me? Are you hearing me? Can you hear me? No. Can you? At the very back? Can you hear me? No? 1, 2, 3. Can you hear me? No? You can? Can you hear me now? There? You can, but they cannot. At the very back, can you hear me? Now you can? Okay, good. All right. So we were, we are on this morning exploring past climates. We are exploring the information from paleoclimate archives. And my task here is to show you, first, that paleoclimate archives are very important in climate change science. Second, what are the main paleoclimate archives? Third, what are the main proxies we use on these paleoclimate archives to reconstruct past climates? And fourth, to show you examples, very important examples in my opinion, of past climates that contribute a lot in the discussion of climate change. In the first part of this talk, we covered the justification, the importance of paleoclimate archives, the main paleoclimate archives, and some of the main proxies used in paleoclimatology / paleoceanography. So the second part of this talk, we will continue on the main proxies used and enter the examples of past climates that are of use, that are extremely important in the context of climate change science. In this very specific portion of the talk, where I'm dealing with proxies, I mentioned a few already. The first ones I mentioned, they were related to properties we can analyze in sediments that reflect conditions from far-field sites, from distant sites. So, when we are analyzing a lactonous material, then I started describing, in this case here, a proxy, a biomarker-specific molecules we can analyze, in this case in marine sediments, to reconstruct sea surface temperatures exactly at the place where we collected the marine sediment core. I showed you that this index called UK37, index of different organic molecules produced mainly by this coccolithophoride here, is linearly related to sea surface temperature. So this is great. In the past, we have let's say we have a marine sediment core. We date, we have the ages of deposition. We can take a sample, say 10 meters deep, and we make the analysis of these molecules, and we calculate the index, and we come up to a value of 0.6. So we know that at that point of time, sea surface temperatures were around, say, 17.5 degrees Celsius. That's excellent. This is very important quantitative way of reconstructing sea surface temperatures. Biomarkers hold many possibilities in terms of reconstructing past environmental properties, and this is yet another example. What I'm showing here is the palmitic acid deuterium isotopic composition Palmitic acid is an unsaturated fatty acid, highly abundant in most aquatic environments. And in this case, with samples collected offshore the Amazon, we have shown a very nice relationship, that's the relationship, to the delta deuterium of the water and the delta deuterium composition of the water itself. It's closely related to salinity. So we have here a proxy for salinity in that portion of the world ocean, namely the equatorial Atlantic, western equatorial Atlantic. So we have temperature, we have salinity, two examples. And we may also assess, now if we are interested on properties from the water column, not environmental property parameters from far-field sites, but environmental parameters close to the depositional sites, we may also analyze microfossils, both their assemblages and their chemical and isotopic composition. Here are some examples of planktonic foraminifera that we may analyze, and if we only look into their assemblages, we may get to very nice bands of occurrence of specific species as we go from the equator towards the high latitudes in both hemispheres. In the topmost panel, we have the most important living species of planktonic foraminifera, zooplankton, dwelling in the uppermost water column in the oceans. All right? These are examples of planktonic foraminifera. This is the scale, so they are small. They are, in the sediments, they are microfossils. Okay? But note that different species have different preferential habitats. And in this case, temperature is the most important factor controlling the abundance of the species, in general terms. Example, in the tropics, we have a lot of Globigerinoides sacculifer. Take a look here on the width of this dark red bar here. On the top, you have the average abundance of the species. As mean annual sea surface temperature decreases, obviously this happens in general terms from the equator towards the north and the south, the width of the bar gets thinner and disappears. It means that this species here, example, this one here, the very top left, occurs mainly in very warm waters, sea surface temperatures, and not occurs anymore at low temperatures, typically of mid to high latitudes. Another example, extreme example, Neogloboquadrina pachyderma. As you can see, very thick bar at temperatures close to zero. So this species completely dominates the upper water column in terms of species of planktonic foraminifera in very high latitudes. And as we progress towards low latitudes and higher sea surface temperatures, the abundance of the species decreases dramatically. By analyzing the abundance of the species of planktonic foraminifera in a specific marine sediment core, we can quantitatively reconstruct sea surface temperature. There are different equations to translate, if you want, or methods, better said. There are different methods to translate abundance of different species towards mean sea surface temperatures or temperature at different depths of the water column. under the microscope, the species are easy to identify in terms of their morphology. As you can see here, they are very different from each other, right? Good. This is an example how we can use the abundance of species of planktonic foraminifera to assess not sea surface temperatures or temperatures at specific water depths, but a specific feature of the climate system that is of interest to us. What is of interest to us here is the Atlantic Intertropical Convergence Zone, is the oceanic counterpart of the Intertropical Convergence Zone. So we were interested in reconstructing the Intertropical Convergence Zone and the oceanic counterpart of it, and we realized that different species of planktonic foraminifera show a pattern, a pattern of distribution that can be used for that. Let us start with Neoglobal quadrina dura, this species here. And bluish means very small abundance of the species in percentage, and reddish means a lot of that species. So what we can see is the species occurring in large amounts in the eastern boundary of the South Atlantic and at a specific bend to the north of the, immediately to the north of the equator. This other species here, Neoglobal quadrina incompta, shows a similar distribution in the Atlantic. This is present-day, modern. Okay? On the other hand, this species here, Globigerina glutinata, show an opposite distribution. Very low in the eastern boundary, but very high in the subtropical gyres. Very low in the very same band as Global quadrina dura and Global quadrina, Neoglobal quadrina incompta show high abundance. So we did a ratio between the percentage of both Neoglobal quadrinas divided by the sum of both Neoglobal quadrinas and Globigerina glutinata. And what we have seen is this color scale here, so very high values of the ratio, marking the position of the Atlantic Intertropical Convergence Zone, the oceanic counterpart of that. Good, so if we have a marine sediment core, and we analyze the ratio between these species, we may infer about the past position of this feature here. There is obviously a mechanistic relationship between the occurrence of the species and the feature we want to assess, namely the Atlantic Intertropical Convergence Zone. Is it possible for a microphone to reach that place?
Hi, thank you. I'm curious to what extent you take into account adaptation over time for these species and how long these species have been around, that type of information.
Yeah, first point, a very good question. I mean, first point is how long these species have been around. Yes, sure, this is a major issue. When we go deeper in time, at a certain moment, we don't find them anymore. So we cannot apply this index anymore. Just an example, right? So this is a major limitation, right? Point. Second, adaptation of the species. Well, this is an issue. This is an issue. But say we are considering the last, in this case, this study did the last 25,000 years. Within the last 25,000 years, we do not expect that much change in terms of adaptation of the species. One of the reasons, therefore, is that the changes we were interested in this study specifically, and but in others as well, some of the others, is that the changes in environmental parameters are very abrupt. And most probably they didn't have enough time to change significantly their ecological preferences. Okay? In longer time scales, this is definitely a major issue to be addressed. Good. And then we come to oxygen-stable isotopes in marine carbonates, for instance, in those same foraminifera, but also on ice cores and continental carbonates like stalagmites. This is a very important proxy. Probably one of the most important proxies, if we can say so. Why can we use oxygen-stable isotopes in carbonates in general, but also in water, in ice? And why it's so important? Because water is very important in the climate system, first. And second, the fractionation that takes place when water shifts or moves, if you want, from one phase to the other, track the conditions in the climate system. Example, imagine we have an interglacial high sea level, and the Earth is going into a glacial period. This happened many times in the past. What is happening? Basically, mean global temperature is decreasing. And linked to that, ice sheets, continental ice sheets are increasing in size. Where is the water coming from? The ice sheets to increase is coming from the oceans. So it's evaporation from the oceans. There is deposited in the continents, and it's not released back to the oceans. So the Earth is going into a glaciation. Imagine on the past, not today, obviously. We are today facing the very opposite situation. Okay, so what happens in the glacial inception, this is the way we call the glacial inception, is that water that is usually being evaporated from the oceans is fractionated. So there are basically three oxygen isotopes, O16, O17, O18. O17 is very rare. So let's take O16 and O18 as the two most important oxygen-stable isotopes. And as evaporation takes place, there is a fractionation. Not a same proportion of available O16 and O18 in the water will be evaporated. But preferentially, molecules of water formed with O16 will evaporate physically. It's easier for those molecules to evaporate. So there will be a concentration of water molecules with O18 in the oceans. So this O16 H2O will precipitate on as snow and be trapped in ever-growing ice sheets as the Earth is going into a glaciation. What happens to the world oceans is that they are getting more enriched in O18 as the Earth continues to go into a glaciation. And then, planktonic foraminifera, for instance, calcifying the upper water column, will record this changing mean oceanic isotopic composition. And as they die, they sink to the bottom of the ocean, and they may deposit into layers that later on, thousands of years or hundreds of thousands of years or even more, we may get them, we may core them, we may sample, we may analyze, we may make stratigraphic models so we know the age of the specific layers. We have an age model, and we may reconstruct past glacials and interglacials. Based on that, very information. Obviously, the opposite of that composition should be found on the ice cores. Because if we have increasingly heavy, because O18 is heavier than O16, water in the oceans, we may have increasingly lighter water in the ice cores. And this indeed happens as the Earth goes into a glacial. And obviously when there is melting of ice sheets, this process is the opposite. Good. Not only this happens, but as a certain cloud of moisture or water vapor, more specifically, travels, there is rain out, there is precipitation going on in the way, and as during precipitation, the heavier isotope now is O18, so it's a molecule of water with 18O as oxygen isotope, precipitates readily, while O16 stays longer in the water vapor. So, as we have rain out, the more precipitation we have, the more rain out will happen, and we will be able to record this in a certain ice core or in a certain stalagmite located far inland, if related to those very close to the site of evaporation. Good. Very important proxy, stable oxygen isotopes. Now the magnesium to calcium ratio in planktonic foraminifera, similarly to the alkenones UK37 index that I showed to you before, we can use the amount of magnesium in the carbonate of those specific shells, those microfossils, to reconstruct calcification temperature. Take this equation here, this relation here, as an example. You see that the incorporation of magnesium is higher as the calcification temperature is higher. Good. So we have this shells of planktonic foraminifera, for example, in a certain marine sediment core. We can analyze the magnesium to calcium ratio on those shells, and we may come up by using one of these relationships here to a specific calcification temperature. Very important proxy for past climates and past environmental conditions is the chemical composition of the air bubbles trapped in ice. As snow deposits in the surface, and as there is more and more snow depositing in a certain place, the air not anymore diffuses readily and freely, but the diffusion gets slower until a certain depth and point in time, if you want, where the air is sealed in the ice. And from that place on, that point on, those bubbles, giving no chemical reactions are taking place on the bubbles. What is not obvious, but let's take it if this is the case. The very chemical composition of these air bubbles here reflect past moments in time when the chemical atmosphere of the chemical composition of the atmosphere, may have been different from today. Well, this is extremely important because we can quantify concentrations with very high degree of certainty of the main greenhouse gases present in the atmosphere, CO2, CH4, and 2O. as I'll show you later on. Biomes are obviously of our interest as well. So if a certain region is occupied by a biome like this one here with conifers, or if a certain region is occupied by a biome like this here, a mangrove, or a high altitude forest in southern Brazil, examples only, this is very different. And this may tell us a lot about how biomes react to climate change. And this may give us then hints to future reactions of biomes to climate change. So we can analyze the pollen trapped and stored in sediments. And by analyzing the pollen, we go back and we reconstruct biomes in the past. Good. So very important proxy as well. Oops. Right. So the list of proxies I showed to you so far is far from being complete. There is a myriad of proxies, depending on your interest, depending on the material you are working with. Say you are working with ice cores. I gave one example, so the chemical composition of the bubbles. But there are many other proxies you could apply there. Examples. You may assess the chemical composition of terrigenous material deposited, by dust input there. We may analyze the isotopic composition of the water itself in relation to the gas, because these are two different media, and we may analyze both, and so on and so forth. Okay? Stalagmites, the same thing. It's not only delta 18O that you may analyze. You may get delta 13C, you may get magnesium, you may get strontium from the carbonate. You may even analyze the tiny amount of water there is in analogy to this situation here, analogy. The tiny amount of water there is trapped within the stalagmites. And we may get the delta 18O of the water from ancient times. We may do the same in marine sediment cores. We may analyze interstitial water and may get directly the isotopic composition of seawater in ancient times. There's a lot of proxies. I gave some just to pave the base, if you want, to the next part of the talk. But before we go there, I want to show now some examples of the second criteria or criterion I told that is necessary a paleoclimate archive to meet before it can be considered a good paleoclimate archive. Okay? And that was the dating. And someone came earlier to me and asked about dating different records. And this is now some examples of dating, getting good age models. This is crucial, as crucial as it can be. So dating is the backbone of paleoclimatology and paleoceanography. We cannot have good paleoclimate, paleoceanographic records without accurate dating.
Thank you. How do you choose the spot to take the sample of sediment and ice core?
Very interesting question. Well, some of these archives, the distribution of them alone, they are limitations. Take ice cores, right? If we look now from the distance, I'll go to the very specific spot, but if we look from the distance, we don't have too many choices in terms of ice cores, right? Well, we go to Antarctica. Well, Antarctica is big, I know, but if we look to the whole globe, Antarctica is not everything, far from that, right? We have Antarctica, we have Greenland, and we have then some other few places where we still have mountain glaciers available, right? So this is a limitation per se. we cannot get obviously as obvious as it can be, but still it's worth mentioning. We cannot get an ice core in let's say southern Brazil. Good. But now in the detail, let's take Antarctica and ice core as an example. Some places in Antarctica are extremely dry. Extremely dry. They have ice cover, but the depositional rate of ice there is very low, extremely low. There are some places that are even in the instrumental record not having deposition at all. So under deflation, it's actually wind are taking out very slowly the material that was once deposited there. Well, if we are interested in reconstructing past climates in high temporal resolution, we cannot go to these places. We would rather choose a place where there is a lot of accumulation. So we take, for instance, places in Antarctica where there is a lot of accumulation of ice. Example, marine sediment cores. Well, we have now much larger choice than ice cores because the oceans cover 70% of the world's surface, and we say, wow, great, so we can basically go 70% of the surface of the globe to take marine cores. It's not exactly that good, the picture. Why that? Again, because rates of deposition are very different from place to place. Take the mid-Atlantic regions, those portions very far from continental margins, usually. In the Atlantic, that's the case. There, because we don't have continental input, we have very low depositional rates. Mean sedimentation rates, there is roughly 1 centimeter per 1,000 years. So it's 1,000 years to deposit 1 centimeter of sediment. On the other hand, on the continental margins, on the slope, as I mentioned before, we have typically 10 centimeters per 1,000 years. So we may get much higher resolution. But then there is another point, not only the issue of resolution, but also the issue of what kind of information I'm trying to reconstruct. Take the example of the Atlantic Intertropical Convergence Zone. You know, that feature I mentioned before, we can reconstruct based on some species of planktonic foraminifera. This one here. This one here. So we are interested on this feature here. Where are we going to go to core? Well, we're not going here. We're not going here. We have to go within its seasonal band of migration and apart from it, but not that far, because if we don't expect and if there is no indication at all that this feature here was located this much south, there's no reason for us to go this much south, right? So this will limit a lot the places where we will core. And because we are interested on very high temporal resolution, we have to go closer to the continents. We cannot go far from the continents. So these are some of the criteria we use to choose one or the other sampling site. Good. So first possibility to date cores, and I'll break for a question again.
Kind of along those same lines, it seems like things can get very complex very quickly because you have deposition from wind as well, which has different sources, different weathering rates, different residence times in the atmosphere compared to deposition from rivers. Is that, I guess, how is that taken into account when thinking about these deposition rates over time? And because over climate time too, seems like those winds that carry sediment would change as well. So it seems like it gets very complex very quickly.
Yeah. Yeah. Paleoclimatology, paleoceanography are sciences per se. They are very complex, as you nicely exemplified in terms of how different components of a certain layer may have very different background history, right? On the other hand, and this, let me go one step back, and this will limit, or let's say this may limit the kind of information we may extract from a certain paleoclimate archive. We have to be, and we are, very critical in terms of what are the types of information that we can extract from these archives. Let's take the very example of different residence time of particles. And I'll give an example in an area I work at a lot. And that's the continental margin of Argentina. The bottom currents there in the ocean, Western South Atlantic, the bottom currents there are very strong. And they transport laterally small compounds easily. But they are not able to transport compounds, let's say, in the size of foraminifera. But they are able to transport particles in the size of silt and clay, obviously, as well. So organic compounds that are very small are easily transported, while larger particles do sink through the water column and get deposited. So, in this situation, imagine we have a marine sediment core collected at 40 degrees south. That's offshore, northern Argentina, if you want. Yeah, 38, 40 degrees south. We have this bottom component of the currents that are very strong and are transporting from the south to the north a lot of organic compounds. So if we apply there alkanones, that proxy for sea surface temperatures, what do we get there at this site at 40 south is much colder temperatures than what would be expected, because these compounds, they have been transported from 50 south, 55 south, and all the way, they have been produced in the water column. Here at 55 south, they are sinking to the water column, and they get transported laterally. And when these currents are not anymore that strong, they get deposited. But the foraminifera, they are larger, they are much denser, so they leave in the calcifying the upper water column here, and they sink to the bottom. So they are deposited on the same layer where first organic compounds are much older because they have been traveling, and they record an information from a far-field site. How we get this? How we get this insight? We date, example, it's not the only way. We date radiocarbon, the foraminifera, and the organic compounds. Not TOC, not total organic carbon, specific compounds. We put together only alkanones, and we do radiocarbon ages. And then we start to see a systematic offset in all ages we do in our core between foraminifera and organic compounds. So we saw, colleagues saw, that there is lateral transport, and the lateral transport results in aging, different ages of the compounds, of the particles on the same layer, so that organic compounds are much older by that much, and the temperatures they record are actually from 10 degrees to the south. Message to take away is, on that core, we cannot use alkanones. We don't use alkanones. We produce a very expensive record, we don't publish it, because we cannot use. But we know now that there is transport, we know now that, all this is. So we assess different residence times, we assess where is the information coming from. And this is an example. It's just one example to show you that we are very much taking care of these issues. So back to dating. There are some possibilities to date paleoclimate archives, and the most, let's say, first one to try to apply is layer counting. Layer counting may be applied to ice cores, may be applied to sediments, may be applied to tree rings, and may be applied to corals. Maybe, not necessarily is. What is necessary to apply layer counting? Well, we have to know how long does it take for two adjacent layers, example, to form or to be deposited. If we do know, and if we are confident about the necessary amount of time for two adjacent layers to be deposited, we can then count back the layers in a certain archive. If we do have one age, and this may be the uppermost layer in a marine core, in a sediment core, or in a coral, this may be age of collection, if it's still active, we may then go back in time and have an age model that is accurate as our counting and as accurate as our assumption of the time that is necessary to deposit two layers can be. Good. Unfortunately, this is not applied in many situations, so that we need other ways of dating. And this brings us to radiometric dating. Well, radiometric dating is based on the principle of radioactive isotopes, the red balls here if you want. The orange are stable isotopes of, say, the same chemical element, and as time progresses, radioactive isotopes in red turn into stable daughter isotopes in blue. And this occurs at a constant ratio. This transformation occurs in a constant ratio. And this ratio can be assessed as the half-life. So the half-life is the necessary amount of time for half of the radioactive isotopes of a certain sample to decay and to produce daughter isotopes. So if we now know the concentration of the daughter and parent isotope, as well as the half-life, it's possible to calculate the age of a certain sample since its formation. That's great. Examples applied typically in paleoclimatology and paleoceanography. Thorium-230 is the parent isotope. Daughter isotope, radium-226. Half-life, 75,000 years. Useful for ages up to 600,000 years. Other example, radiocarbon. So carbon-14, daughter isotope, nitrogen-14, half-life 5.8 thousand years, useful for ages up to 50,000 years. Good, perfect. This is a very nice way to date paleoclimate archives. There's a third possibility. Because these methods go back to a certain age, there are obviously others that go back to different ages, but they are not all applied to all kinds of records. Take, for instance, an ice core. I cannot apply thorium-230 to date an ice core because it's simply not present. This system simply does not work in ice cores. This works nicely in stalagmites. This works nicely in, say, marine cores, lacustrine cores. This works nicely in 3 rings. But it's not working in many other records, and it's not working for ages higher than 50,000 years. And many of our paleoclimate reconstructions are going much farther back in time. So what do we do then? So this is an example of stratigraphic tuning. So third main possibility to date paleoclimate archives, stratigraphic tuning. So what is this? This is like tuning, the old radio where you are, you are tuning the station you want to hear, and then, okay, you go a little, okay, then you come back, okay, this is the best frequency. You're tuning your receiver to the available stations or whatever. So, example here. There is, in order to perform stratigraphic tuning, the age model of the record you are going to tune your record to has to be known by any other mean. For instance, thorium dating or whatever possibility. And here, the example shows a reference record of stable oxygen isotopic composition of benthic foraminifera. So those microorganisms living at the bottom of the ocean, they calcify. We can analyze delta oxygen isotopic composition on those shells. And this record here is dated. So it is fixed to an age model. And these are the ages going to 250, 240,000 years before the present to the present, right to left. So what this shows, it basically shows glacial, interglacial variability. It shows ice volume. So today, low ice volume. In the past, a lot of ice volume. You see higher ratios of delta 18O, means a lot of 18O in the ocean. Obviously, this happens when there is a lot of 16O in continental glaciers. Makes sense. Great. And then we have here, for instance, and here more specifically, the glacial inception that I mentioned to you in some steps if you want, okay? This will be first step, this is second step, this is third step. This is the last glacial maximum here, when we have the largest ice sheets in the world for the last glaciation. All right, and we have these 3 records, marine cores coming from different places in the equatorial Atlantic, 5 north, 9 north, 12 degrees north, and we don't have age models for them, but we have the delta 18O composition of the benthic foraminifera, and we can tie. Look how these features are similar to that features. This is because the benthic foraminifera living here and here and here, they were under the same, let's say they were suffering, if you want suffering, from the same global changes as those. So ice, continental ice was increasing or decreasing, and they were having the same effects on the delta. They were seeing and recording the same effects on delta 18O composition. So we can use tie points and say, well, this trend here is very much that trend there. When we go from not the last, but the glacial maximum before the last towards the last interglacial. The present interglacial is here, but the last interglacial is here. So this trend here is this one. So we can use tie points. We say, well, I can export the age of this one here to this, and to this as well. So the age model from a different core is imported to the core without an age model by correlating a specific record of both cores that are mechanistically related. Good. Third possibility of dating. And now we are done, and we are going to paleoclimate records. My selection of paleoclimate records. So we start with greenhouse gas variations and past climate responses to them. And here I'm showing to you 8 the longest available time series of concentration of CO2, one of the most important greenhouse gases in the atmosphere. In green, here, we have carbon dioxide concentration in the atmosphere, reconstructed for the last 800,000 years. This is a huge effort from the paleoclimate community to come up with this record. It's very high resolution, extremely well dated, and it goes back 800,000 years. Folks, this is a lot. What we can see here, example, is variations, apparently cyclic, for high and low, between high and low concentrations. And the values, the envelope of variability is roughly 280 ppm to 180 ppm. So it's an interval of 100 ppm that is being respected throughout the last 800,000 years of natural climate variability on this planet we call Earth. But now we are over 400 ppm. So 120 ppm higher than the highest boundary of the last 800,000 years. Okay? We have other records here. Tropical sea surface temperatures reconstructed from marine cores. In anomaly, not in absolute values. Okay? We have Antarctic temperatures in anomaly as well. Okay, it's delta T, it's an anomaly in relation to modern or pre-industrial. We have the benthic foraminifera delta 18O. Now, this is very much what I showed you before, but I only showed you 240,000 years of this. Note that the x-axis shifts. Okay, sometimes I show you the present, the past to the right, and the present to the left, and sometimes just to make the lecture more interesting and less boring, I put the opposite way, so the past is on the left and the present is on the right. So paleoclimatologists usually do this. Past on the right and present on the left. But when we are trying to communicate to other communities, then we shift. This only makes things more complicated because then on a certain lecture like this one, I have both, right? So I have this one that was actually a paper for the paleoceanographic community, but then this one here, there is a output of the IPCC AR5 that is obviously wishing to communicate with other communities, and then we shift. So this only makes things more funny, right? Okay. And we have sea level here, all right? And there's a small box showing the rate of change of temperature for the very last deglaciation. Deglaciation is when we go out of the last glacial into the present interglacial. All right, my aim here is to show that it's a matter of fact. Present, this is 2011, all right? Concentrations of the atmospheric greenhouse gases, in this case CO2, exceed the range of concentrations recorded in ice cores during the past 800,000 years. There is no point out of this. This is simply a matter of fact. We cannot argue against this. It's simply and clearly here. All right? Obviously, 400 ppm as we are now, or higher than that, has major impacts on the climate system. What we can see from this relationship, for instance, CO2 and sea level. We can see that when CO2 is low, sea level is at the minimum. Take another example. Take this one here. sea level is very low. Take this one here. Sea level is, again, very low. Take high CO2 periods in the past. This interglacial here, high sea level. Take this interglacial here, high sea level. There is a mechanistically link between both, right? This is important. There is a mechanistically link between CO2 and temperatures, both tropical temperatures and high latitude temperatures. And we'll stress this relationship because this is extremely relevant for climate change science later on. And it's now, not later on, but now. So this is now a detailed study on the last deglaciation, okay? The transition from the last glacial maximum to the present. Note in terms of sea level was 120 meters below pre-industrial and raised to pre-industrial values pretty quickly, as we have seen at the beginning of this lecture. So this is now a zoom in into the last, in the period between 22,000 years before the present and 8,000 years before the present. Is the deglaciation. The deglaciation is this transition here. What is shown here? Okay, let's start with yellow. Yellow is CO2 composition in the global atmosphere. Mean composition in the global atmosphere. So minimum value 180, maximum to 60 to 65 to 70. Okay, ppm V volume. Blue, a proxy for global temperatures. Anomalies as well. Easier to work with anomalies than with absolute values. Blue, only look at the blue now, is reconstructed global temperature, mean global temperatures. It's not modeled. It's based on alkanon, magnesium, calcium, GDGTs, and each and every other record that passed through very strict quality control and is integrated now with a complex algorithm to get the spatial representation of every record correct. And you see this trend here, right? And then there is here in red, changes in Antarctic temperature, mean. Note that CO2 starts to increase more significantly before temperatures. So this is a very important piece of information to tell us that changes in atmospheric CO2 concentration play an important role in glacial interglacial cycles. So we do believe that this glacial, interglacial, glacial, interglacial, glacial, interglacial cyclicity is related to changes in orbital parameters like eccentricity of the Earth's orbit, like obliquity in the Earth axis, and precession of, as a third main movement of the Earth. But CO2 play an important role on this. That said, we may go back to different moments in the Earth history where we had a similar orbital configuration, but we didn't came out of a certain glaciation. We only come out of a certain glaciation when obviously the orbital conditions are appropriate and CO2 increases, making it possible for global temperatures to break out of glaciations and reach interglacials. Very important. Absolutely. These are let's say, the Milankovitch cycles. Changes in eccentricity, obliquity, and precession.
What is the cause of the natural increase on CO2 concentrations in the interglacial periods?
Good. Excellent question. Oh, yeah, it is. I mean, did everyone got the question? No manifestations, I assume, is yes, everyone got it, right? Well, but I will repeat anyway. He asked about the cause of this huge increase of 100 ppm on CO2 concentration during the last deglaciation. I mean, why did CO2 concentration in the atmosphere increase that much without any anthropogenic role, or let's say input? Now we also have, since the pre-industrial 100 ppm, basically 100 ppm of increase in CO2 in the atmosphere, but this is all anthropogenic. Okay, between 18 and 10,000 years before the present, we did have humans on Earth, obviously, but ecological footprint was very small. Let's put it this way. So the reason that under glacial conditions, first, the oceans are much colder, like the surface of the Earth as well, and colder waters can dissolve much more gases. So the oceans were taking up a lot of CO2. So much of the CO2 that was not in the atmosphere during the last glacial maximum or previous glacial maximums were mainly in the oceans. And why they come then back to the atmosphere? Because temperature is increasing. But then you may say, well, but this is chicken or egg. I mean, you just told that CO2 is increasing first and temperature second. So how is it possible that decreased solubility because of higher temperatures triggers release of CO2? And now we come to a topic that I love, and it's changes in the strength of a circulation in the Atlantic called the meridional overturning circulation. And you will see later on that because there is a major halt on this circulation in the Atlantic, there is an increased warming in Antarctica. High latitudes in the northern hemisphere get cold. It's transient. But Antarctica gets warm. I will show this in very detail. I'm just showing you a snapshot now, a teaser. We have a migration of the circumantarctic belts, climatic belts, and oceanic belts to the south. As this happens, the southern westerly winds increase its strength, so there is more upwelling in the Southern Ocean. And these upwelled waters, they have a lot of CO2. And then CO2 goes back to the atmosphere in huge amounts. And one of the projections of future climate change is a decrease in the strength of this meridional overturning circulation and the southward migration of the westerlies and the circumantarctic climatic and oceanographic belts. And you can imagine what could be a consequence of that. Good. But we'll go back in detail on that. So during the last deglaciation, it's very likely that global mean temperature increased by 3 to 8 degrees Celsius, while the mean rate of global warming was very likely 0.3 to 0.8 per 1,000 years. Take a look at this. We are going out of a glaciation, 100 ppm, huge changes in the world landscape. Imagine 3,000 meters of ice above North America that we don't have anymore. Imagine 3,000 meters, yes. Imagine 130 meters less of water in the oceans. I mean, we could go from France to England to UK without having to swim. We could go from Indonesia to Singapore without swimming. We could, I mean, most of the continental shelves were exposed, right? Biomes changed dramatically. But still, the rate of warming during the deglaciation going from the LGM to the interglacial was 0.3 to 0.8 increase of mean global temperature per 1,000 years. I mean, when we talk about modern climate change and post-industrial climate change, we have figures that are dramatically higher than this. Two periods were marked by faster warming, two periods of the deglaciation, likely 1 to 1.5 degrees Celsius per 1,000 years. Although regionally and on shorter time scales, higher rates may have occurred. All right. So still about greenhouse gas variations and past climate responses, with medium confidence we can say that global mean surface temperature was significantly above pre-industrial levels during several past periods characterized by high atmospheric CO2 concentrations. So the geological record tells us that high CO2 leads to high continental and oceanic temperatures. There are a myriad of records to show that. I already showed this image here. Briefly summarize it. So global sea level changes during past warm periods. You see the rate of change of the natural, let's say the climate system, can be much higher than what we have been seeing. This raises a note of caution. Because if this happens again, well, our dependence to certain circumstances will be disrupted dramatically. So the current rate of global mean sea level change starting in the late 19th, early 20th century is, with medium confidence, unusually high in the context of centennial scale variations of the last 2 millennia, but very low if compared to other periods in the geological history. Again, about sea level, this is, in red, mean estimated sea level. For a period of time, take a look here, 135 to 115,000 years before the present. It's the last interglacial. The interglacial before the one we live now. And this is 0, is pre-industrial, let's say modern sea level. You can see levels of 5 meters higher than pre-industrial sea level on the last interglacial. So there is very high confidence that the maximum global sea level during the last interglacial, say from 129 to 116,000 years before the present, was for several thousand years at least 5 meters higher than present, and high confidence that it did not exceed 10 meters. Okay, it was not higher than 10 meters. Oh, nice, 10 meters. Oh, between 5 and 10. We are worried about half a meter. We have to be very much worried about half a meter of sea level rise. We have already went through 12, 13 millimeters globally. So 5 meters, between 5 and 10, okay. So, and the contribution from Greenland was 1.4 to 4.3. And there was some contribution from Antarctica as well. All right. What about observed recent climate change in the context of interglacial climate variability? Well, this is very important. This is global temperature on the last 1,200 years. Because we instrumental records, we have this. The last 100 years, 150 years, depending on the region you look, depending on well, how long the records are. But based on geological archives, biological archives, we can go back much further back in time. And this is the situation we see. So present-day levels are much higher than what we have seen the last 1,200 meters. And this is a statement from IPCC. There is high confidence that annual mean surface warming since the 20th century has reversed long-term cooling trends of the past 5,000 years. I'm showing here only 1,200. In mid to high latitudes of the northern hemisphere. Okay, this is northern hemisphere. Sorry about that. This is northern hemisphere temperatures, not global temperatures, only northern hemisphere temperature. Okay. In gray, reconstructed based on proxies and paleoclimate archives, and in red and blue, simulated with models. They agree very well. And the envelope of the models. You see the thick bar, the thick line, and the thin lines. They agree very well. And this is very different from what happened without anthropogenic influence. Still about observed recent climate change in the context of interglacial climate variability, there is high confidence for droughts during the last millennium of greater magnitude and longer duration than those observed since the beginning of the 20th century in many regions. So extremes and the magnitude of extremes may not be well represented in the instrumental record. That's why we look into paleoclimate records to get a full amplitude of extremes. And obviously, extremes may be getting even more extreme as global temperature rises. With high confidence, floods larger than those recorded since 19th century occurred during the past 5 centuries in northern and central Europe, western Mediterranean region, and eastern Asia. Let's now go back to abrupt climate change and the possible irreversibility of some changes. And this is interesting because we can look into a specific event occurring at 8.2 thousand years before the present that was abrupt and that caused significant changes in the strength of that circulation I mentioned to you. It decreases a lot. There were major changes in the Atlantic intermediate water temperatures, decreasing significantly during this period here. And there are beautiful records showing a major decrease in sea surface temperature based on those foraminifera assemblages, planktonic foraminifera assemblages, in the Nordic seas. You see, 10.8 going to 9.2 degrees Celsius. This is a lot. And for instance, delta 80 in Greenland, showing changes in temperature around Greenland. We can say that with high confidence, the interglacial mode of Atlantic meridional overturning circulation can recover, because it is recovering from a short-term freshwater input into the subpolar North Atlantic. On top of that, we can say that it's virtually certain that orbital forcing will be unable to trigger widespread glaciation during the next 1,000 years. So if we were kind of waiting for the next glaciation to come in order to solve the problems of climate change, we can forget that. Paleoclimate records indicate that for orbital configurations close to the present one, glacial inception, so the start of a glaciation, only occurred for atmospheric CO2 concentrations significantly lower than pre-industrial. So with this kind of CO2, N2O, CH4 concentrations we have in the atmosphere, we will not go into another glaciation. Climate models simulate no glacial inception during the next 50,000 years if CO2 concentrations remains above 300 ppm. So this is absolutely not a solution. Back to abrupt climate change and reversibility, confidence in the link between changes in North Atlantic climate and low latitude precipitation patterns has increased. And now I will go into the topic of, in more detail, of changes in the Atlantic meridional overturning circulation that has direct links to the CO2, change in CO2 concentration during the last deglaciation. So here we have a north-south transect for the uppermost 5,000 meters of the water column in the Atlantic for salinity. Okay? Salinity values, this is the scale. And we see low salinity waters called AAIW. This is Antarctic intermediate water flowing to the north. Beneath it, we see North Atlantic deep water flowing to the south. And at the bottom of the ocean in the Atlantic, we have Antarctic bottom water flowing to the north. What this tells us, these two major flows of water are very closely related to each other. And they compose a circulation that we call the Atlantic meridional overturning circulation. There is a lot of water being transported. For instance, in the surface layer of the ocean, pretty south, there is 16 sphere drops of water being transported across the whole South Atlantic to the north. One sphere drop is 10 to the 6 cubic meters per second. By the way, one sphere drop is basically the discharge of all rivers to the ocean. Okay? So we have 16 times all rivers discharge flowing to the north in the surface, and in the bottom, in the deeper layers, we have 23 sphere drops flowing to the south. This flow here is basically this here, while this flow here is basically this flow here, and the topmost layer of the ocean. Is this okay? This continues to the 25 south, and there is this 16 sphere drops of flow of water, surface waters towards the very high latitudes of the North Atlantic. And these waters sink, they suffer downwelling at two specific places, Labrador Sea and Nordic, Norway, Iceland, Greenland seas, and flow back as deep layer here in blue to the south. What I'm showing here through the Drake Passage and to the south of Africa is not the flow of the Antarctic circumpolar current, not at all, but the amount of water flowing into the Atlantic sector of the Southern Ocean that ends up entering the South Atlantic, okay, and is not flowing through all the way around Antarctica. And this is what is the best estimations for the leakage of Gulias waters into the South Atlantic as well. So the inflow of Indian Ocean high salinity waters preconditions the Atlantic for North Atlantic deep water formation, but this meridional circulation in the Atlantic is not only responsible for transporting a lot of water, it's also responsible for transporting a lot of heat. It was quantified that at the same transect there is a net northward transport of heat, what is an anomaly regarding the Pacific, the South Pacific and the Southern Indian Ocean, to the north of 0.3 petawatts. A petawatt is 10 to the 15 watts. Just for your information, I mean, the largest Brazilian, today, yeah, I think so, yeah, largest Brazilian hydroelectricity plant generates 0.00014 petawatts. So this is a lot of energy. And at 25 north, there is this transport of heat amounts to 1.3 petawatts. So what if this circulation weakens in the future, and what if had weakened in the past? We have to put this huge amount of energy somewhere in the climate system. IPCC class AR5 models suggest to the end of the century a significant decrease in the strength of the Atlantic meridional overturning circulation. The decrease can be between 20 and 30% in scenario RCP 4.5 and 36 to 44% under RCP 8.5. So we can have, according to these simulations, up to 44 decrease in strength of this circulation. Obviously, this huge amount of heat that is under strong AMOC transported to the North Atlantic and the Northern Hemisphere will not anymore be transported and to the Northern Hemisphere, and this may have a major impact on the global climate. Indeed, different papers have already been raising the importance of the Atlantic meridional overturning circulation, and that the 10-year long instrumental record, please note that we only have slightly more than 10 years of monitoring of this circulation in the ocean. We don't go 100 years as some precipitation records do, some temperature records do. I mean, we only go 10 years. Shows inevitable surprises. I'll show you a snapshot of these surprises. And others are already showing an exceptional 20th century slowdown in the Atlantic meridional overturning circulation. That is the manifestation of this, most probably, already. So this is the inevitable surprises that Strokos and Bryden in 2015 showed in Science. This is the longest series of monitoring of this circulation in the Atlantic. It only goes back to 2005. 12 years now. Okay? Smoothed running average in red, and what we can see is probably a long-term decrease and a large seasonality. Instrumental records are definitely too short to appropriately investigate changes in the Atlantic meridional overturning circulation. Is this indeed a decreasing strength? Is this a cycle? So we can look back to the past to see what may have happened in the past and what were the impacts of major decreases in strength. And we will do that. But before we do that, I show you this paper published in Science Advances this year. So this paper, differently from this author here, that do not show a collapse of the Atlantic meridional overturning circulation as long as the simulation goes. These authors here, they argue that it was an overlooked possibility of a collapse of the Atlantic meridional overturning circulation in warming climate. So they corrected CCSM3 for a certain bias, and what I got is compared to a control run where there was no fixing of this bias, there is a major decrease within the next 300, 400 years, basically going to very small values, meaning a possible collapse of the AMOC. Indeed, some authors like Lenton and co-workers suggested that Atlantic deep water formation, and this is where those waters sink to deeper depths and flow back to the South Atlantic, is a tipping element in the climate system. So tipping elements are those features that if a certain threshold is surpassed, the climate will work significantly different than they did before. It's not a linear relationship, it's a threshold. So formation of North Atlantic deep water, a tipping element in the climate system whose threshold could be reached within this century. Well, this is very serious. There are different tipping elements in the climate system, and different authors list different elements. This is a very good suggestion from Lenton and co-authors. And now let's see what happened in the past. Because in the past, there were periods of collapse of the Atlantic meridional overturning circulation. And what were the consequences of those collapses? If the models are now having some trouble to simulate these nonlinear responses, let us look to the past and see what were the responses of past environments to major collapse. And how we know that there were collapses? Well, this started back in the late 80s, in the early 90s, as Heinrich and Bond and co-authors, they saw the North Atlantic major layers of ice-rafted debris. Imagine a core sitting far from Europe and from North America, showing layers of high concentration of fragments transported by icebergs. Well, it cannot be differently. I mean, icebergs must have been transported all the way to this place and melted here, so that the rock fragments transported by these icebergs were deposited here. Wind is not able to transport them, and there is no other media that can transport those rock fragments there. So these authors, they saw that, well, many records in the North Atlantic show synchronously show layers with high concentration of ice-rafted debris. Wow! And they did many measurements, and they have shown, for instance, they called these layers age events. For age for Heinrich. The first one that in 1988 described these layers. So layers rich in detrital carbonate. So this is material coming from land. Okay? Deposited in the ocean. And when there was one of those layers, they also saw that, for instance, the abundance of a species called Neoglobal quadrina pachyderma, one of those species I showed you before, that likes a lot cold waters, was very high. You see, higher abundance of pachyderma in relation to the whole assemblage. So very cold waters, all right? Percentage of detrital carbonate, because the rock fragments here were carbonates, but not foraminifera, rock carbonates from continent, was high. All right. In different cores, amount of lithic grains high. Say, well, the possibility they envisioned by then, and was a great one, to explain these layers was that there was a major discharge of icebergs from glaciers coming from North America, melting in the high latitudes of the North Atlantic. And this fresh water delivered to the North Atlantic disrupted the Atlantic meridional overturning circulation. Because if you have very low salinity in the upper water column, on the place where this water mass should be sinking, it's too light. It's not dense enough to sink, and it's staying at the surface. So you stop this belt of circulation. All right? And when we stop this belt of circulation, what do? We do not transport. The climate system is not anymore transporting to the north this 1.3 petawatts of heat, and this heat has to be somewhere in the climate system. It stays in the south. And look how interesting it is. If we compare Delta 18O records from Greenland and from Antarctica, both hints for temperature over Greenland and Antarctica for the last deglaciation, we see that when the thermohaline circulation or the Atlantic meridional overturning circulation, in this case I will consider them similar features. When it's on, we have a warm Greenland and a cold Antarctica. When it's then turning off, we have a cold Greenland and a warm Antarctica. When it's then turned on again, the heat is transported to the north. So we have a warm Greenland and a cold Antarctica, and so on. But this has consequences not only to Greenland and Antarctica, but for instance, off southeastern South America, we see that sea surface temperatures increased markedly during the gray bar here. The gray bar here is exactly a period of collapse of the Atlantic meridional overturning circulation. As temperatures in the northern hemisphere, Iberian margin, decrease, temperatures in the western equatorial Atlantic increase. In here, the western South Atlantic increase. Southernmost eastern South Atlantic increase as well. There is what we call a bipolar seesaw. Consequences are not only there for temperature, but they are there also for precipitation. The changed sea surface temperature gradient in the Atlantic, in the equatorial Atlantic, leads to a southward shift of the intertropical convergence zone, as we can show here, delta D, here in red, delta D of plant waxes, a proxy for precipitation, over northeastern Brazil, because this sediment core here was collected off northeastern Brazil. We see that the red dots here are going towards more negative values. And they stay very negative as long as there is a shutdown or a significant weakening of the Atlantic meridional overturning circulation. Black is model run, and green in this case, red or blue is proxy. So major increase in precipitation over northeastern Brazil during periods of collapse of the of the Atlantic meridional overturning circulation. And we showed that intertropical convergence zone over the western Atlantic closely followed the change in meridional sea surface temperature gradient. And this is a synchronous and linear relationship. As we go from the LGM in the light blue here to the dark blue, we see an increase in temperature, in precipitation, and we see accordingly a change in the sea surface temperature gradient in the Atlantic. All right, but we have seen other features, as I mentioned to you before. For instance, the stratification of the upper water column of northeastern Brazil, there is a very shallow mixed layer, whereas to the north of the equator, there is a much deeper mixed layer. The depth of the mixed layer there is very much related to the position of the Atlantic intertropical convergence zone. These are only examples to show how big the impacts were. And what about the deep water geometry in the Atlantic during the last glacial maximum? Because this goes back to how much CO2 we can put on these water masses. Not only temperature, but the ventilation age or the rate of ventilation of these bottom waters will significantly control or impact the concentration of CO2 in the atmosphere. So this is present-day modern, let's say. Present-day is not exactly the case. It's Holocene situation of the Atlantic, 40 degrees north, 40 south, from 1,000 meters to 5,000 meters in the water column, based on epsilon neodymium. This is autogenic, not in the heterogeneous phase. And this is the situation for the LGM. So we see a marked north-south gradient at deep waters, suggesting sustained production of North Atlantic deep water and another northern source of water mass here, an intermediate water depth. So here we calculate the percentage of North Atlantic deep water today and during the LGM. For instance, at a site 20 north, 400 meters water depth, we had between 70 and 60% of North Atlantic deep water, while for the same site in the modern ocean, we have from 80 to 90% of North Atlantic deep water. So this corroborates the statement I just made, and this is a more easily to understand cartoon of what may have happened with glacial circulation in the Atlantic compared to today's situation. You see, there is still North Atlantic deep water being produced, but the flow of this water mass is extremely sluggish, and thus the ventilation of this water mass is very low, and so we are able to put much more CO2 on that water mass. It's not exchanging with the atmosphere as it is today, for instance. So a greater amount of respired carbon, and this is very much the CO2 that is not anymore in the atmosphere, it's synthesized into organic matter in the photic zone, sinks to the bottom of the ocean, and is respired, being in the form of CO2, and it's and total dissolved in organic carbon, must have been stored in the abyssal Atlantic during the last glacial maximum by a sluggish deep overturning cell comprised of well-mixed northern and southern sources of waters. All right, so we are now at the end of this lecture, and there are three references that I would like to point to you if you are interested on the topic. So first one is from Lowy and co-authors, 2007, Understanding Quaternary Climate Change. This is a short overview, very interesting in my opinion. All of them obviously are extremely interesting. Then we go into a more robust and longer text. That's IPCC AR5, Chapter 5, Climate on Paleoclimate, Masson Del Monte and co-authors. And for those that are very interested, I would then suggest a textbook from Bill Rudiman, 2014, Earth's Climate, Past and Future. This is outstanding. All of them are outstanding. Different lengths, different scopes. You may find the best one suited to you. And feel free to contact me if you want. Many thanks for your attention. I think there's a question over there.
Thank you. That was really interesting and enlightening. Appreciate it. It wasn't quite. I learned a lot through understanding more about the circulation patterns in the ocean and controlling CO2 levels, but it wasn't quite clear to me how it resolves the chicken and the egg problem, because the CO2 leads the temperature, but it seems like temperature is what's driving the changes in this circulation. Thank you.
Okay, good. The chicken and egg issue, this is a very good one. In the case of the last deglaciation, for deglaciations to occur, we have to have a certain orbital configuration. Without a certain orbital configuration, we cannot start the deglaciation. But the deglaciation, only with a certain orbital configuration, will probably not progress into a full deglaciation if there is not a huge input of CO2 to the atmosphere. Chacun and co-authors in 2012, and this is the plot I showed that in the last deglaciation specifically, we have the rate of increase in CO2 increases a lot, and then temperature follows. How this happened? This happened the following. When the Atlantic meridional overturning circulation was, decreased its strength dramatically during the deglaciation. Remember, icebergs in the North Atlantic, melting of icebergs, very low salinities in the uppermost layer of the high latitudes of the North Atlantic, so that, the downwelling could not happen anymore because you have a layer of fresh water. It's not dense enough to sink. It may be very cold, but it's not dense enough to sink. So you halt, you stop, let's put it this way, or you decrease the strength a lot of the meridional overturning circulation. When this happens, the 1.3 petawatts, or a fraction of it, is not anymore transported to the North Atlantic because you don't have anymore the means to transport it. So this huge amount of heat is trapped in the South Atlantic, Antarctica also, and other, in the Southern Hemisphere, let's put it this way. When this happens, climatic belts and oceanographic belts, they shift to the south. As they shift to the south, what happens is that we have a steeper gradient in sea surface temperature from the pole to the mid-latitudes in the Southern Hemisphere. When you have a steeper gradient, you strengthen the westerlies, for instance. Let's take now specifically the westerlies. You strengthen the westerlies. By strengthening the westerlies, we increase upwelling and ventilation of those old and CO2-rich waters close to Antarctica. And they get to the surface. As they get to the surface, there's no sea ice because it's warm there, and they exchange gases with the atmosphere, and they release a lot of CO2. because the concentration in the water is high and the concentration in the atmosphere is low. We are in the LGM and going out of the LGM. So there's a lot of CO2 going to the atmosphere. As this huge amount of CO2 goes to the atmosphere, greenhouse gas, we have global increase in temperature. And this is the necessary, let's say, phenomenon to complete the deglaciation. So, in a few words, during periods of slowdown of the Atlantic meridional overturning circulation of the last glacial, we observe an increase in CO2 concentration in the atmosphere due to this process I described, mainly. Okay?
Thank you very much, Prof. Mine is on the greenhouse gas concentration. You have illustrated it for carbon dioxide and for methane and nitrous oxide. But you have not talked about or shown a record of concentration of water vapor. And also, if so, maybe, what is the role? What is its role in the glacial and interglacial cycles? So that's one. The second one, it's just an inquisitive question about the sampling which you talked about. Especially, you were talking about the oceans only. All the examples cited from Atlantic, from Pacific, are samples only obtained in oceans or also other freshwater bodies like lakes and rivers can be good samples of study for paleoclimate? Because there are some rivers which have dried up and a history is there why they have dried up. And also some lakes, there is a decrease in water levels, and a history is there. So, perhaps your comment is relevant there. Thank you.
Yeah, thank you for the questions. Let's start with the water vapor. Water vapor is rather controlled by, the concentration of water vapor in the atmosphere is rather controlled by temperature. So as temperature increases, it's possible to have more water vapor in the atmosphere. As temperature decreases, we have less water vapor in the atmosphere. And this is not what happens with the CO2 in terms of the values we have in present-day climate and what is expected for future climate and what we had for, let's say, glacials. So despite being despite the fact that water vapor is greenhouse gas, its concentration in the atmosphere is controlled by temperature. So if we have higher temperature than as we are expected to have in the future, we will be able to have more water vapor in the atmosphere. And this is, by the way, a very worrisome information because water in the atmosphere as vapor is latent heat, and latent heat is energy, and more energy in the atmosphere is very problematic for extreme climatic events. So that's for water vapor. Second, other archives. Well, I also showed records from ice cores, and I also showed a few records from continents. And what I showed here in terms of records is the editor's cut. It's a selection. There are plenty of records coming from these 5 main kinds of archives that I mentioned before, namely ice cores, tree rings, corals, sediments, both lacustrine and marine, and caves. All of them are or may be excellent paleoclimate archives. There are great records coming from former lakes, lakes that are now dry. We have example very close to, within the city of São Paulo. There's this Colonia crater, the southernmost portion of the city, where now it's dry, but there is a great record there, paleoclimate record, where part of it was a lake. So, yeah, this is for the different archives. There are plenty of different archives, and all of them have advantages and disadvantages. And this was my selection of archives.
So, Professor Fitzgerald, many thank you for your lecture. I have a question based on the paleoclimate records and the growing evidence about current climatic conditions. Do you consider that the Earth is entering in a new historical period, as some refers to the Anthropocene, for example?
Okay. Yeah, sure. I absolutely agree. Yes, this is the short answer. Yes. The role of the humans now surpassed, to my opinion, the natural phenomena controlling surface processes in the Earth, so that we could call now for another interval of time in Earth history, namely the Anthropocene.
Thank you very much for the lecture. I want to know your opinion about some study that was published in geology, and you were explaining that under glacial conditions, the ocean get colder, and then the CO2 can stabilize more in the ocean. And they were relating this to algae. They were saying that for some reason that they don't know why, the algae can sink more CO2 in this cold ocean. What's your opinion about it?
Well, these are two different things, and we have to differentiate. One is the solubility of CO2 in the water, and here is a physical process, and you can take a parcel of water completely void of organic matter and change its temperature, and you will see that you'll be able to put more or less CO2 on it. So this is pure physical process, is solubility of CO2, in this case, in water according to temperature. And second is a possible, let's say, reaction of algae to different concentrations of CO2 in the atmosphere. What we have, let's say the basic rationale we have for the LGM to explain the very low CO2 concentration in the atmosphere during the LGM is based on, as I mentioned before, colder temperatures, so you can solubilize more CO2, sluggish ventilation of bottom waters, so you don't, there is less ventilation of this bottom water masses with the atmosphere, so transiently this makes possible for the climate system to store more CO2 in the ocean. And third, and I didn't mention this before, obviously this is a science per se as I started this talk, and we cannot cover every topic in 3 hours, and this is not the aim as well, but there was apparently more dust being deposited in the Southern Ocean during the LGM, and dust, atmospheric dust coming from Patagonia, coming from Australia, coming from Southern Africa. Deposited in the Southern Ocean, this triggers primary productivity in the surface layer of the ocean, and this increased primary productivity takes out CO2 while dissolved in organic carbon first, and this then makes it possible for more CO2 to be dissolved from the atmosphere into the ocean. And when these algae die, they sink to the bottom of the ocean, and part of this organic matter is not decomposed, so it traps CO2. also. So increased primary productivity in the Southern Ocean probably as well helped to decrease CO2 concentration in the atmosphere as we progressed from the last interglacial to the LGM. The gradual extension of sea ice around Antarctica also played a role, if we want to now name the most important factors, because as we have more sea ice around Antarctica, the ventilation of these water masses are less efficient because we have a cover, a lid on the ocean that do not allow a very efficient water-air exchange of gases. Okay?
Hello. Well, thank you, first of all. And regarding the intensification and weakening of the Atlantic meridional overturning circulation and the Greenland, Antarctica dipole, I was wondering if there's a study relating the warm-cold phases of the Antarctica with the increase and decrease of sea level.
Okay, let me see if I understood correctly the question. If there is studies relating this change in temperature to changes in sea level.
Right.
Okay. But you mean because of possible continental ice in Antarctica that is being...
Yeah, specifically in middle to high latitudes.
Okay, but you mean because of water being released from melting ice sheets in Antarctica?
Exactly.
Okay. Yes, there is a relationship like this, but the amplitude of change in sea level is not that large. Okay? Yeah.
I have a question about terrestrial contribution of CO2 as we're moving in and out of glacials and interglacial cycles. I thought I remembered from Rudimann's book that he talked about essentially Milankovitch cycling forcing, essentially the aspect of the northern hemisphere to the sun causing releases in methane and CO2 as like swamps released more methane or had more or less water and temperature. Is that also perhaps a role in the progression of CO2 in front of temperature for some of the glacial interglacial cycles that you showed today?
Okay, let me see if I understood the question. The question is relates or would ask for a relationship between, if there is or how it is, between release of greenhouse gases from high latitudes, continental portions of the continents in the high latitudes of obviously the northern hemisphere, right? Yeah. During deglaciations, well, first, methane is then coming as the most important greenhouse gas, okay? And not anymore CO2, but first of all, methane. And yes, during the deglaciation, there's a huge increase in methane in the atmosphere. I didn't show it, this data. And wetlands and areas that were previously we had permafrost may have contributed, most probably have contributed significantly to the increase, in this case, in the methane concentration in the atmosphere. But note that since these areas are located in the northern hemisphere, they have probably not contributed to the early increase because during that early increase, continental temperatures in the high latitudes of the North Atlantic were cold. And that's specifically when the circulation, when the Atlantic meridional overturning circulation is very weak, the high latitudes of the North Atlantic experienced glacial temperatures, again, although we are already in the deglaciation. But later on, they definitely contributed significantly to increase in methane, more specifically, increasing methane concentration in the atmosphere. So, well, folks, if this is not the case, we don't have any more questions, we are ready for lunch. Thank you very much.